honors course?
That's correct, yes. It's one of the honors capstone courses, which are a little bit, in my opinion, a little bit more hands-on and a little bit more out of the classroom in a sense.
Okay.
We tend to meet down near St. Petersburg just about every week, even though we're from the Florida or the Tampa campus.
Okay.
Because we work at museum trying to preserve a lot of the artifacts and re-update their exhibits.
So what's your major?
I major in microbiology.
Okay.
And then I do environmental science and policy.
Okay.
Integrative animal biology.
Good. So, you know, oceanography is integrated biology. Because biology is the whole shebang. It's not just biology. I always like to joke about that, but it's true.
Yeah, definitely.
So, good. All right. So I'm yours.
All right. Is the camera rolling?
Yep, that's good.
All right. Sounds good. All right. Thank you for meeting with us and giving us your time today. Can you tell us a little bit about yourself and your research?
Sure. So my name is Robert Weisberg, and I'm a professor of physical oceanography, which means I don't know anything about animals or plants, but I do know something about how the water moves around. And it's the movement of the water in the ocean that determines the properties in which the animals and plants live. So the physical oceanography is actually a very essential part of ecology.
All right. What are you currently working on in regards to red tide?
So we've learned over the years that red tide, which has a very complicated natural history, will flourish under certain conditions, but not under other conditions. And those conditions really are determined by the ocean circulation. And so there's, I like to say that the organism biology and the physics of the ocean circulation are equally important. Each provides a necessary condition for a bloom to develop, but neither alone is sufficient. So I interact with biologists that are studying the organism biology, and I provide the ocean circulation physics, and together we actually are trying to understand how this natural phenomena actually functions, and try to predict on a seasonal basis whether we'll have a bad one or not. And then once we have one, we make short-term predictions of where it will go.
All right. Why are you researching red tide as opposed to any other topic?
Well, it's a very, it has a very long history on the west coast of Florida. It's extremely important for tourism, for fisheries, and so of the various natural phenomena that we do study, it happens to be one of great, great importance for the state. So that's part of the motivation. It's also very interesting because we live next to a portion of the ocean called the West Florida Continental Shelf, which is as wide as the state of Florida. And because it's so wide, there are portions of the West Florida Shelf that tend to be nutrient deplete. So the biologists have a word for that. It's called oligotrophic. And but when you look at the fishing industry, the tourist industry, these algal blooms that we get, you have to ask the question: how is it possible for an oligotrophic shelf to have such copious fisheries resources, to have these major blooms of various types of algae? So from a scientific perspective, it becomes a very interesting place to work. And so, those two things together, the mystery of why an oligotrophic shelf can be so productive, and the importance of these various phenomena to the economy of the state of Florida, provides motivation to study them.
That makes a lot of sense. You previously mentioned a little bit about how the tides affect red tide. Can you give us a little bit more detail about what specifically causes red tide?
Sure. So it's actually not tides. Tides are one aspect of the ocean circulation. It's probably the most studied aspect because going back in ancient times, Euler was studying tides. And so mariners have been studying tides since they started putting a ship in the water. But the tides really don't move things over great distances. So what we really have to be concerned with is how the local winds and heating and cooling, and also how the adjacent deep ocean is driving the circulation on this very broad West Florida continental shelf. So the winds, if they're blowing from the north, can actually cause water to move offshore, and that water gets replaced by new water moving onshore. We call that an upwelling circulation. If the winds are out of the south, they'll actually cause water to move onshore at the surface, offshore at the bottom. We call that a downwelling circulation. Either of those scenarios will transport material across the continental shelf. So, let's say that we can put nutrients from land into the ocean, and those nutrients will be consumed within a fairly narrow band. We can also put nutrients onto the shelf in the deep water, and they'll be consumed over a fairly narrow band. That leaves this big portion in the middle that generally tends to be nutrient deeply. If we can start a circulation that's going to move new materials across the shelf, then we can change the nutrient state of that middle portion, the portion that's generally oligotrophic. So the winds can do that, but they tend to vary. You know, sometimes it's out of north, sometimes out of south, so things kind of go back and forth a little bit, but not enough. There's another thing that can force the circulation, and that's the Gulf of Mexico loop current, which comes in through the Yucatan, loops around, goes out the Straits of Florida. And when the loop current comes in contact with this portion of the West Florida shelf, near the dry Tortugas, it can actually set the entire shelf in motion in an upwelling, favorable sense. And when it does that for a long period of time. It doesn't just happen and go away. In fact, we're in one of those protracted upwelling situations right now. So if we're in an upwelling situation for long enough, we can actually take new water with higher nutrients from here and move it all the way across to here. And anything that's in that water will similarly move with it. And that's what's happening right now with the red tide. So we had conditions in spring, early summer, very conducive to formation of a new bloom for 2018. And then towards the end of July, the loop current started to touch over here, instituted an upwelling circulation. And so whatever had been growing out here has been arriving at our beaches. And that's why we're having such a bad red tide this year.
All right, that makes sense. So red tide, this organism which is feeding on these nutrients, how does it affect the wildlife and ecology of the beaches?
So red tide, it's you know, we all have a way of making a living. So you're hoping to become a journalist, you'll make a living doing that. Maybe you won't. One of the ways that red tide makes a living is it kills fish with its toxins. That's why it has toxins. And then as those fish decay, they release nutrients into the water, and the red tide can then feed off of those decaying fish. So one of the ways in which red tide actually makes its living is by killing fish. That's why it's a harmful algae. These toxins are also dangerous to any other living organism. So manatees, you know, they breathe right into the surface. They're inhaling those toxins, so manatees get sick by it. The manatees eat the foliage in shallow water, and that foliage may have the red tide toxin. So manatees, you know, are very seriously impacted. Just think of these poor porpoises that are swimming around, breathing right at the surface. So they keep breathing in these toxins. And so, same thing with turtles. So anything that is either ingesting the toxins either through eating or assimilating the toxins through their gills, you know, taking the oxygen out of the water, can be seriously impacted by these toxins. Now, as fish die and sink down to the bottom, the whole process of decay consumes oxygen, so you can deplete the oxygen near the bottom. If that gets low enough, then all the organisms living along the bottom will die because there's no oxygen for them. So there's a lot of different ways that the red tide organism can have a very disastrous impact on the ecology. Now, having said that, red tide's been with us forever. And so it, you know, it evolved for a reason. I mean, I don't really know what that reason is, but it certainly did. And so you have to ask the question, what if we could eradicate it, get rid of it? And as humans, we wouldn't have to suffer the nuisance of the red tide when we have a bloom. But what would that do to the ecosystem? What would that remove that may actually be important for the ecosystem? So that's something that's a mystery. We haven't really thought through that. I mean, I have a couple of ideas, but I'm a physical oceanographer, I'm not a biologist, but I actually do have a couple of ideas of what that might be, which I won't speculate on because it's out of my field. But I mean, we don't like to get stung by bees, but if we didn't have bees, nothing would get pollinated. We don't like to get, we don't like our house to get eaten by a termite, but without that, you know, there wouldn't be soil. So everything has a purpose, even if it's a nuisance.
That makes sense. Speaking about it being a nuisance to humans, what are some of the harmful effects that it can have for humans, visitors, and residents along the beaches?
Sure. Well, you know, it's very unpleasant. Nobody likes to smell rotting fish. Nobody likes to inhale the toxins and get the kind of throat irritation. And for people that are asthmatic, it can actually be quite dangerous. For anybody with some kind of underlying respiratory ailment, it could be quite dangerous. That's one thing. And so what we find during a bad red tide bloom is no one wants to go to the beach. The restaurants on St. Pete Beach have really been hurting. People aren't going to eat, and people aren't going to the hotels.